So yeah, good morning all. We'll try to continue our discussion switch reluctance motors, that converters. So we need separate converters for this switch reluctance motor, because okay, here it works on the principle of variable reluctance. It always follows the minimum reluctance path here. So not the field interaction that we normally see in the traditional synchronous machines and other things here. So let's be more specific here. Here torque production is independent of current polarity, and that's why we repeat specialized converter here. And one more thing is, here standard AC inverters we don't is not suitable here. And here in the switch reluctance motor, next point is it requires converters that precisely control the current pulses, okay, and based on the rotor position. Here we need to continuously monitor the rotor position, and accordingly that current pulses has to be controlled here, and that's why we require separate converters here. Okay, in converters here, stator windings are connected in series with the converters for switches here. Directly it is connected here. Let's try to see few switches here. Okay, so yeah, let's actually get into the different topologies here. We have four topologies here. So SR converters can be categorized by the relation of number of semiconductor switches here. So we might be studied already have discussed this number of switches here, that one be semi-controlled, uncontrolled, fully controlled, different types of switches will be there here. And we can even control number of phases also. Number of pole pairs indirectly depends will be decide number of pole pairs decides the number of motor phases here. Unlike in the traditional synchronous machine, we restrict only for 3 phases here. Here number of pole pairs, if 4 pole pairs are there, we can able to make a 4-phase machine here. So power converters here. So coming to the okay, so whenever we are trying to make any converter here, it has to satisfy following requirements here. What is that? Okay, so an excited pole should be demagnetized before entry of the generating zone here. So here whenever any winding is excited here or energized here, it has to be completely de-energized here. These are the mandatory conditions here, and each phase of SRM switch reluctance motor should be excited separately here. Each pole pair has to be given supplied separately here. And coming to that, freewheeling action should be achieved during the chopping period, that is turn off period here. And freewheeling action, we'll try to discuss all this. We'll get into actually all these topics in detail in the this coming 4 main groups here. And demagnetizing energy should be fed back to the source here in the turn off period here. Okay, for the next sequence to be operated here. And circuit should be completely cost effective here. So the major 4 points are very important here. Okay, so there are four types that we actually discussed here. That is 2M switch here, two switches for phase here, and M switch here, 1 switch for phase here, M plus 1 switch here. There is 1 additional switch for entire converter here. So number of phases is for each phase we use one switch, and in addition to that we use one more switch here, 1.5 M switch here. That is suitable for even number of machines here. Let's actually get into this here. So I will be discussing the first one in a detailed manner, and okay, and you can able to continue with the other topics in the easier manner here. So first one is 2M switch converter here. You can see the diagram here which is specified here. So this is the DC supply. Okay, basically why I require an inverter here, because let's try to consider an example of EV here, where in the EV here we use the supply as a battery here. From battery the supply the electrical power has to reach to the motor, and the motor has to drive the vehicle here. Yes sir, motor has to drive the vehicle here. What is the battery here? It is in DC supply here. Okay, and can I directly give this DC supply to the motor? Like the switch reluctance motor is completely AC motor. So I need an inverter. Which converts a DC supply into AC supply here. That too specific here. It has to excite separately for each phase, and that's what we discussed here. And for that reason, I'm using a DC supply, and I'm using different switches which can be able to convert a DC supply into AC supply here. So, and this is the first type is the asymmetric bridge converter here, asymmetric bridge here. So here all these are nothing but the motor winding phases here. For your better understanding, I have shown the another diagram also, where you can see the different windings here. Let's assume that this is, as we discussed previously here, this is A dash, B dash, okay, C dash here. So these are the 3 pole pairs here. How many phases we are making here? We are making 3 phases here. Okay, 3 phases here. This is first phase, this is second phase, and this is third phase here. For each phase here, how many switches are used here? 2 M switches are there. This is 1, 3, 5, 4, 6, 2 here. Okay, 4, 6, 2, or you can change your notations as per your requirement here. So it is just for understand here. S1, S3, S5, S2, S4, S6 here. These are the switches here. How many switches here? We are using two switches for each phase here. And purpose of diodes is to provide a feedback path for the switches here. Okay. And here the major difference is nothing but instead of drawing the motor here, I'm using this placing the winding. So we assume that this A phase, B phase, A phase winding and B phase winding and C phase represents the switch reluctance motor windings here. Okay. And coming to the topology here. Just now I discussed that two phases for here. We can use we can use two phases for two switches for each phase here, and two diodes for each phase here. The purpose of the diodes is to provide the feedback for the current flow here and in the feedback current option here. And what is the purpose of converter here? So it has to give supply to the each winding as per the requirement here. Okay, it manipulates here. Okay, converters, the converter or inverter. Okay, we say that specifically it is inverter. Okay, a converter can be rectifier or inverter here. Specifically converter here it is inverter which manipulates the DC voltage to AC voltage for the specific pole pairs of the SR motor here. So again, independent phase control is also we need to have here. Each phase is energized separately and each phase is given to separate here. So we will try to see the operation here. Okay. First we will try to see that when the supply is okay, instead of drawing this complete diagram here, I am just switching here. So okay, yeah. Okay, so now what I will try to do here, first when this, let's say I am to be more specific, I am only concentrating on this A phase here. When S1 and the S1 is on and S2 is on, okay, then DC supply is directly connected to the phase A winding here, so that directly power flow will be stored in the inductor here, and here inductor stored energy will be plus minus in this manner. Okay, and this for the better understanding, I am just used only this case here. This is the DC supply. Okay, and inductor will be stored energy stored, the coil winding is stored the energy in the manner here, plus minus here. Okay, now here we are using the hysteresis current control loop here. Okay, here we are using what is the current control method here? It is hysteresis current control method here. So what does this mean here? Here current is controlled using the between the certain range here. When the current reaches the maximum value, the switches are automatically disconnected. When the currents are reached to the minimum value, the switches are reduced here. This is what it is specified here. You can see that hysteresis current control here. Yeah, this is the maximum and this is the minimum here. I max and this is I minimum here. When the current is reached to maximum here, then you can see that this S1 and S2 are disconnected when it is reached to the maximum. When the current reaches to maximum here, S1 and S2 are off. When the currents are reached to this minimum here, then what happens here? S1 and S2 are off here. When it is on, then D1 and D2 will be D2 will be on here. Okay, so totally there is a freewheeling action takes place, and directly the normal motoring action, the supply the power will be fed from the supply to the winding here. That is the normal case here. Okay, so this is the first case where when the S1 and S2 are on here. Let's assume that the current is minimum and is okay. Then when the switches are on here, when the switches are here, as you see the direction here, that the power is directly fed from the supply to this phase A winding here. Okay, and now here when the current is increased to the maximum here, when the current is changed to the IA current is changed to the maximum value, then as I said that S1 and S2 will be off here. S1 and S2 will be off here. Now when S1 and S2 will be off here, then D1 and D2 will be on. And initially, previously, whatever the energy stored, that is inductor, when it will try to interchange its polarity here, okay, at the time of freewheeling action. That means, okay, the direction of current will be like this. I'll try to change the color. Okay, so the freewheeling action will be takes place, and what happens here, as the D1 and D2 will be on here, okay, the current direction will continue to be remain in the same case here, but only the polarity changes. The voltage polarity reverses. Voltage polarity reverses. Current direction remains same here, voltage polarity reverses, and previously it was plus minus, now it is changed to minus plus here, and current direction remains same here, current direction remains same. So it will use as the D1 D2 and supply, and it is the okay, and the power flow is okay, power flow energy will be given to this supplier here. In this manner the energy is required here. Okay, so a freewheeling action is taking place here. Okay, and yeah, so this is only for phase A winding. Similarly, the same process will be happens to the B and C phases also. Okay, so, okay, let's try to discuss the waveforms here. Okay, so almost the waveforms is similar to the other cases also. Okay, this is first one is LA, inductance of the A phase here, IA is the armature current here, VA is the voltage here, and S1 S2 switching operation sequences is there here. So normally here inductance will be minimum, L inductance will be minimum in unaligned positions here. So here when the rotor and stator are not in same axis, then the inductance will be minimum here, and inductance will be keeps on increasing when it is slowly aligning here. Inductance will be maximum when it is aligned here, and this is the difference here. Rotor and when the inductance is aligned here, the value is increasing here. Okay, that's what the case here. And coming to this, you can see that the current is controlled, the phase A winding current is controlled between the minimum and maximum here. You can see that when the current is minimum here, due to as S1 and S2 are here, the current increases, and once it reaches here, S1 S2 will be off here, and when it is on here, the voltage VA will be positive. When it is off here, due to the voltage polarity reverses, so the it will be shifted to the negative side here. It will be negative here. Okay, and in that situation D1 D2 will be operated here. So it's not D1 D2 is not specified in the graphs here. This is how the working principle of this, and it is clearly explained here also, so you can go through once it is required here. Okay, this is the complete operation, and what are the conclusions here? What I can conclude from here, hysteresis current is majorly used here, where it is controlling the current from the minimum and maximum range here, in between the minimum and maximum here. Doesn't control magnetic control here, relatively simple implementation, and with this we can able to achieve the good dynamic performance here. Freewheeling function here, diodes provide the free inductive current to flow through the switches are off here. Yeah, control flexibility here, if we are going with the independent phase control here, and we are also using the hysteresis control here, so that the performance will be good here. This is one method of topology here. And coming to the second here, we will try to discuss the second conversion is M switch SR converter. M switch SR converter, that is, which is also called as R-dump converter here. M switch and SR converter, which is also called as R-dump converter here. In this case here, okay, here previously it was 2 M switches here. Now that means for one phase, okay, for one phase I am using one switch. So here how many let's assume that here 3 pole pairs are there here. So that means 3 phases, 3 switches are used for 3 phases. This is for A phase, this is for B phase, and this is for C phase here. So I have shown you the diagram here. That means this is the motor winding for A phase, B phase, and C phase here. Okay, as same that DC supply is connected here, and one switch is S1, S2, S3, 3 switches are connected, and D1, D2, D3 are 3 diodes are connected for the to provide the feedback here, feedback path or freewheeling action here. So in addition, one resistance and one capacitance is also connected here. Okay, and as we are using 3 switches for 3-phase machine, we call it as N switch converter here. It is also called as R-dump converter. Why it is called as R-dump converter? Let me try to justify this conclusion here. Okay, when okay, first we'll try to discuss that, and then I'll try to justify why it is called as R-dump converter here. Okay, yeah, I'll just this. Okay, so let's try to mean in each SR type here, each phase is energized independently. So let's try to show here okay, what is actually happening here. When S1 is on, here, then what happens here, the supply is directly connected to this switch phase A winding, and current, this is the current IA direction here, and this is the VA direction, and the coil gets energized here. Okay, and as I discussed that when the A phase winding has to be when the power supply has to be connected to the B phase here, whatever the energy stored in the A phase, that has to be completely de-energized here, and that's why I am using the freewheeling action. This is the condition which we already discussed here. So when I'm switching from A phase to the B phase here for connecting the supply here, whatever the energy stored in the coil or in the winding here, that has to be completely de-energized, and that's why I'm turning off S1 switch and turning on buying the D1 diode here. It is de-energizing here, or whether it may be energy is wasting here, or else it is fed back to the supply here. Okay, so this is the power case when S1 is on here. Now I'm just erasing this here so that we can able to understand in a better manner. Okay, so when S1 is off, okay, when S1 is off here, then what happens here? When S1 is off, then D1 will be on here. D1 will be, as diode is condition here, the inductor changes its polarity here, and the current has to flow in the same path here. Current direction will remain same. Okay, now here what happens here? The current will flow through this D1, and it will passes through resistance, and it passes again back to this coil phase A winding here. In this manner, it forms a closed path here. So it will try to flow, the current flows through this, whatever the energy stored in this phase A winding, it will try to flow through the resistance. Okay, and it forming a closed path. In this manner, the freewheeling action takes place here. Here I can also say that whatever the energy stored in the inductor in the on period, when the switch one is on period here, that will be dissipated, that will be wasted in terms of in the resistor, and that's why it is called as R-dump converter. Whatever the energy stored here in the freewheeling action time, the energy is wasted in the resistance here, and that's why it is called as R-dump converter here. Okay, and I hope you okay, that is a justification of R-dump converter. Okay, there is a justification of R-dump converter, and rest everything is same here. So major thing is here resistance is whatever the energy, the purpose is to whatever the energy stored in the on period, that has to be dissipated in the resistor during the off period here. And there is one more thing to be discussed about the capacitor. The energy stored, the energy used to charge the capacitor and dissipated in the resistor here. This is the purpose of a capacitor here. Coming to the waveforms here, the waveforms are similar to that. Here again we are using the hysteresis current control loop also. So we already discussed that in the previous case here. So inductance is minimum under the unaligned position here, and it is maximum in the it will be maximum in the aligned position. So there will be variation in the inductance here with respect to the rotor to the stator here, and current is controlled between the maximum position to the minimum position. When IA is minimum here, when IA is minimum, S1 will be on here. When IA is maximum, when S1 will be off here. When S1 will be off here, then D1 will be on here, and that's what here specified here. When IA is minimum, S1 is on here, and we can see that voltage is positive here. When S1 is off, that is when D1 is on, and D1 is on here. Okay, when D1 is on here, we can see that as the inductor coil changes its polarity here, inductor voltage is negative here. In this, and these are the operating waveforms here, and complete explanation is also given here. And we'll try to discuss the advantages as well as the drawbacks here. So here, what are the major advantages here? Minimum components are required for this. Okay, and it uses only one switch for one switch and for one diode here. Okay, and it majorly reduces the complexity as well as switching frequency is also reduced here. And what are the drawbacks here? Inefficient drawbacks here. Okay, inefficient drawbacks here. Okay. Inefficient operation. Okay, inefficient operation here. That means the energy is not utilizing here. Whatever the energy that has to be not regenerative, it is completely wasted in terms of dumping here. That means as we are throwing our waste into the dump yard, so similarly the energy is dissipated in the resistance here, and that so reducing the overall efficiency. Inflexible control here, as there is an absence of zero voltage here. We can see that a negative voltage here. Okay, in the freewheeling action, or then so it loses the control flexibility here. And major drawback here, it is selection of resistance here. The value of resistance is critical in selection here. So if the value is very small, then it leads to the longer current fall time, and if the value is very large, it increases the turn of transient voltage here. And this is the overall explanation of second type here, M converter here. Let's quickly proceed to the third type here. So it is that is M+1 switch converter here. It is C-dump converter here. What are the drawbacks that we see in the R-dump converter? That is, the power is wasted in the resistor, and it's not fed back to the supply here. We'll try to make use of the power that is stored in the the winding here under the when the switches are off here. So what is this M1 switch here? That is nothing but for each phase I'm using for M phases I'm using M switches, and in addition that I'm using one more switch here, one more switch for the overall circuit here. Okay, you can see that this is VDC, Cin, LR, DR. This is CD, capacitance CD here. This is TR. This is the additional switch here. You can see the T1, T2, T3, T4 are the switches that are used for each phase here. And let's assume that here I am using the 4 pole pairs. That means I am using A dash pole pair, B dash pole pair, C dash pole pair, D dash pole pair here. Total 4 pole pairs are 8 poles. Okay, so that how many phases will be generated here? 4 phases will be generated here. Okay, so the same phase A, phase B, phase C, phase D. For 4 pole pairs here, that means I'm using each switch separately, T1, T2, T3, T4 here, and similarly D1 for D1, D2, D3, D4 for separately for D1, T1 for phase A, D2, D2 for phase B, D3, D3 for phase C, D4 for phase D here. Okay, and coming to the switch configuration here. Okay, coming to the this is what we discussed here, and TR is used separately for all the operation here. And coming to that capacitance, what is, in addition to this, we are also using some other things here. So capacitor, okay, is used for the smooth ripples of the DC voltage here. Inductors is to store the energy when the current flows through it here. That is LR here, LR. And coming to the DR here, it is used for the freewheeling operation here. Okay, it is used for the freewheeling operation. Ultimately, like in the other cases also, here independent phase control, each phase is energized separately here. Okay, and to get for the precise control of the switch reluctance meter, in order to control in a better manner, we are using independent phase control here. Coming to this operation here, so it will be difficult if I try to show the same operation through this circuit here. Like you can able to, okay. So it will be a little bit difficult, so that just to have this, I am trying to split the circuit here in this manner. So coming to this operation here, so here I'll try to assume in the different cases here, when T1 TR is the when T1 and TR are on, when T1 and TR are off here, in this phase here the power flow is from the phase supplied to the phase winding here. This is the motor phase winding for, let's say I'm assuming for the A phase here. Okay, let's assume that T1 is on. So majorly we are concerned about the T1 switch here. So in both the cases I will assume that T1 switch is on. When the T1 switch is on here, the power is directly fed to the phase winding here. As you see here, power is directly switch. Okay, this T1 switch will be on, so that it forms a short circuit here. The power is directly fed to the phase A here. Now even in some cases, let's say the TR is also on here. When TR is also on here, the power is again fed to the phase A winding here, and the motor and through T1 switch. And here when TR switch is there, the power is fed back to the TR switch, and the inductor gets charged here. So ultimately what I need to understand here, that the phase A winding is energized here, and here again we are using the hysteresis control current control loop here. Like you see that here it is between the maximum and when the current reaches to the maximum here, the switches the particular phase switches will be turned off, and other switches has to be on here. So energy transfer, coming to this energy transfer here. Now when what is happening here, okay, in the first case, okay, when the first case I am assuming that the current IA current is minimum, and T1 is on, and we are making the IA current to maximum here. We are making the IA current to maximum here. Okay, when IA current is maximum here, then what happens here, ultimately this T1 will be made off. The T1 will be made off here. Okay, this T1 will be made off here, and this is all done by the hysteresis current we already discussed here. Now when T1 is off, okay, when T1 is off here, now you can see that so previously the current is to pass through this path here. Now the current is not flowing through this here. Now here when T1 is off here, the same power from the DC supply has to be flowing through this capacitor here, and it is fed back to this supply here. It has to, whenever current has to flow here, it should be able to form a closed path here. So this plus or minus this here, what's the purpose of this CD here? This capacitor stores the energy power. Okay, the capacitor stores the energy here. That means the inductor Okay, the capacitor stores the energy here. Okay. Okay, yeah, let me continue here. So as we discussed that in the when T1 is on, the inductor, the coil, the phase winding coil is energized here. Now when suddenly when current is maximum here, when current is maximum here, when T1 is off here, then energy stored in the inductor, or in the phase A winding has to dissipate here. Further, it changes its polarity and current will continues to flow here, and during this process it charges the capacitor here. Okay, the current will be flowing in the same path here. It charges the capacitor here. The capacitor is placed between the phase A winding and the supply here. So that whatever the energy stored here, it has to completely demagnetize and it has to made to zero here, so that energy stored in inductor will be stored in the capacitor, and and this process, the inductor voltage polarity changes here and current continues to same here, and this is the freewheeling freewheeling action. That means energy stored in inductor has to be dissipated. This is what actually here. And once this capacitor we call this as a dump capacitor here. Once this dump capacitor is sufficiently charged here, then we'll make sure that okay, TR or TR switch is on here. TR switch, whatever the TR switch is, it is made to turn here. So we just discussing about three different cases here. This is the first one is T1 is on here, and when that is IA is minimum. Once IA is maximum, then what happens here? T1 will be off here. Once T1 is off here, during this time, what happens here? VA will be reverses, okay, and CD charges, and once CD is charging maximum here, CD charges to the maximum here, then TR switch will be on here. Once TR switch is on here, whatever the energy stored in the capacitor, that will be fed back to the DC supply, and it's forming a closed path here. That will be fed back to the DC supply. Always power is fed back to the DC supply from the positive side here. So in this manner, like we discussed in the previous case, in the R-dump converter, the power is simply energy wasted in the resistor in terms of heat here. Whereas here, whatever the energy stored in the inductor, that is temporarily stored in the capacitor CD, and after once the TR switch is on here, it is fed back to the supply here, and in this manner we can able to achieve the regenerative braking here. Okay, in this manner we can able to achieve the regenerative braking, or else the power is not wasted in the turn off period. It is fed back again to the supply, and so that ultimately the efficiency and performance will be increases here. This is the major concern and major advantage of this type of converter, and that's why it is called as M1 switch converter, or else it is called as C-dump converter. Why it is called as C-dump is capacitor used temporarily stores energy and it fed back to the supply here. Okay, and coming to this characteristics, similarly the waveforms is similar to that of here, inductance, current, okay, T1 TR switch here. Okay, when T1 TR switch is there, we already discussed in different detailed cases here. And both T1 and TR is on, that is mode 1, and when T1 is off, that is mode 2, and TR is on, that is mode 3. We have discussed in detail here. You can go through this. Okay, and history is current control here. This IA star is the reference current here. Okay, so it is clearly explained here. And coming to the advantages here, it is the number of switches are reduced compared to the 2M switch here, so that switching losses will be reduced here, and the circuit complexity will be less here, and energy recovery is done in the so I guess previously I told you that regenerative braking here, instead of that, its better word is energy recovery. Energy recovery is done by this capacitor C-dump mechanism here. And coming to the disadvantage here, negative voltage is less. Okay, we have a negative voltage here. Negative voltage is limited because of the difference between the capacitor voltage and the DC supply voltage here. Okay, this can slow down the current commutation. With this limited negative voltage, the current commutation can be reduces here. Okay, so compared to the previous cases, C-dump converter is very better here. Okay, and let's try to proceed with the last one here, that is 1.5 M switch converter here. So what is this 1.5 switch converter here? That is, I will try to use even this converter is used for the even number of phases only. Here we have it is comparatively better to the 2M switches here. Okay, and here we have SX switch and SY switch here. These are the switches which are common switch for the two phases here. So here I am considering the 4 phases. That means A dash, B dash, C dash, D dash pole pairs here. For A dash and B dash, I'm using Sx which is common. For C dash and D dash, I'm using Sy switch common here. Okay, so totally I'm using S1, S2, S3, S4, four switches are there. Okay, and in addition to that, there is a common switch for two phases here. Okay, for each two even pair, even pair here, I'm using extra switch here. That is for the A phase and B phase, I'm using Sx switch, and C phase and D phase, I'm using Sy switch here. And similarly, all D1, D2, D3, D4 switches diodes will be there for freewheeling action here. And coming for the Sx and similarly DX and DY. DY diodes will be also used for the freewheeling action. Okay, this is about the topology here, and it is also called as even. It is specifically used for the even number of phases only, because I cannot use for 3 phases. I cannot use 1.5 switches, like 1.5 switches here. That's why it is used for even phases only. Okay, it is used for even phases. That is 4 phase 6 for 4 phases. How many switches I'm using here? 6 switches. For 8 phases, 12 switches. Similar in that manner. Okay. So operating waveforms, first we'll try to see the operation here. Okay. So for a better understanding, we'll only restrict ourselves to phase A winding here. When Sx switch is on and S1 switch is also on here, when both switches are on here, then power from the DC supply will be fed to this phase A winding, and through this, and it forms a closed path here. In this manner, phase A winding energy stores here, energy stores in this case here. This is normal case here. Okay. So now coming to this, when again I will use the same hysteresis current control method here. When here in the both the cases, I will assume that current IA is minimum. When IA is reaches to the maximum position here, what happens here? When IA is reaches to the maximum here, then S1 switch will be off here. You can see that here it is clearly specified here. So I'll change the color so that you have a better understanding. Okay. So here, this is when it is reaching here. When it is reaching this, till this point, S1 is on here. Till this point, S1 is on here. When current reaches to the maximum value, what is happening here? S1 will be off. S1 will be off here. And you can see that throughout the operation, Sx is on here. So that means during the on period as well as off period, Sx will be on here. Okay, I can able to conclude that this Sx will be continuously off here. Okay. Now when S1 is off here, when S1 is off, I'll try to show that here. When S1 will be off here, whatever the energy stored here, that has to dissipate here. So first thing is inductor polarity changes here. It changes its polarity. Okay, and current direction remains same here. So the current direction has to flow in the same manner. Okay, current direction has to flow in the same manner. So you can see that the current will be flowing through this inductor, and it is flowing through D1. Again, as Sx is already on here, it is flowing through this manner. In this manner, it is forming a closed path here. Okay, in this manner, it is forming a closed path, and so that whatever the in this manner, it is forming a closed path, and energy will be dissipates here. Okay, yeah, I'm sorry, I just told you in the wrong way. So let me try to tell you here. For the energy recovery process has to happen here. For this, the polarity changes here, and whatever the energy stored here, that will be flows through the disk D1. And during this process, the energy recovered energy will be processed through this DC supply. The power will be recovered to the DC supply, and again it flows through DX switch, and power is fed back here. In this manner, whatever the energy stored in the phase A winding, that will be fed back to this DC supply. So I can say that energy recovery, when energy recovery takes place here. Energy recovery takes place here, and this is what actually for each phase separately here. So I can conclude that. So throughout the operation of phase A, Sx will be on. Similarly, for throughout the operation of phase B also, Sx will be on here. And when current is maximum, S1 will be on, and when the current is minimum, the S1 will be. When the current is reached to maximum, S1 will be off, and current is reached to minimum, S1 will be on here. The process will remain same here, and this is current control and rotor align and unaligned position. Everything will be remain same here. Okay, and this and why it is called as 1.5 mm here. Sx will be used for the both phase A as well as phase B, and Sy will be used for phase C and phase D here. And this is all about the explanation here, energy recovery concept here. So, and coming to the advantages here. So here major advantage, it is the number of switches will be reduced here. So compared to this, it is in between this 2m will be more number of switches used and m switches will be less number of switches here. M 1.5 will be okay, m plus 1 switches, and there is one more thing is m here. So here it lies in between this, and the energy recovery also takes place here. Reduced number of switches here, independent phase control will be there here. Coming to the disadvantages here, we have to use only for even phases only. Not if I want to go with the 3 phase here, that is not suitable for this 1.5 m here. So higher switching rate is here. So the shade switches, that is SX and SY switches has to be with higher ratings here, because it is used for case here. So this is the overall conclusion for this. Overall conclusion of all the 4 types here: 2m, m switch, m1 plus and 1 point switch here. So how many switches are for phase, each phase is used here? 2, 1, 1.1, that is for shade, and shade for 2 phases, SX and SY here. Control flexibility, cost, complexity, efficiency, applications and advantages. You can go through all this, and this concludes the SR converter topologies here. Yeah, thank you.